Hi guys, and we will solve some problems, the first 7 problems in this worksheet 3, right? But as you see on this question, the second one was in the second worksheet, and this was also in the previous worksheet, so I will not solve them again, of course. Right, so let's start with this one. Now we're given a function which is defined piecewise, right? Now, when x is not equal to -2, it's defined by this quotient. It's fraction 1 over x plus 2. And if x equals to -2, it's defined by this constant function, which is 1. Now, we will determine if the function is continuous or not at this given point, -2, right? You know already very well the graph of the function 1 over x, right? You already know that this is the graph of 1 over x. So to sketch that, we need to shift this graph 2 units to the left. So we have this graph, okay? The graph of this function. And you see f of x is defined on this point -2. It's defined by this. So this point is also included in the graph of the function. Now, what about the limit of f? When we're approaching -2 from the left, we see the graph of the function is approaching to -infinity. And if we're approaching -2 from the right, you see its limit is approaching to infinity. So it has no limit. It means the function f of x is not continuous at that given point. Okay. Now, what about this one? So let's solve that too. Right, so we have this function. This is the question 1 and part D. Right, so the function is given by this. It's defined by cosine x if x is less than 0, and it's defined by 0 if x is equal to 1, and 1 minus x squared if x is greater than 0. Okay, it's not 1, by the way, it's 0. Okay, this should be equal to 0. Okay, and of course a is equal to 0 here, so we will determine if the function is continuous or not at this point. Okay, so let's check first the limit of the function. When x is approaching 0 from left, the function is defined by cosinus, right, as you see. So here we have cosinus x. So we just plug x equals to 0 and get cosinus 0 is equal to 1. So we get 1. And from right, the function is defined by, now let's write that directly. The function is defined by 1 minus x squared. Just plug x equals to 0 and we will get again 1. So it means the function has limit at that point 0 and it's equal to 1. All right. Now, but you see that the function is defined by 0 at that point 0, right? So it means the limit of the function at that point 0 is 1, and it's not equal to its value at that point. So it means f is discontinuous again at that point. What about its graph? We just sketch its graph. You see, when x is less than 0, cosinus x already, you know, at the point 0, it's 1, but we have empty dot as we don't have equality there. And you know the graph of the cosinus already. What's that point? This is minus pi over 2, and this is minus pi. This is minus 1. For example, this is minus 3 pi over 2, right? This is cosinus. And when when x equals to 0, it gets the point 0. So we have this dot. What about this function? When x is greater than 0, we have this 1 minus x squared, which is this. And this is, of course, 1. Okay. How do we sketch that? You already know the graph of x squared, right? This one is x squared. And minus x squared is this one. Minus x squared. And if we want to add 1, we need to shift this graph 1 unit upwards. So here we have this function, right? Now, as from this graph also, we can see we're approaching 0 from left and right. We get 1 as a limit, and it's defined by 0 here. So it's discontinuous, right? All right, we're done with the first question. As I said before, these were in the second worksheet. So what about this part? Let's solve that. We will determine if the given function, this f of x, has a removable discontinuity or not at the given point A, right? Which is 2 here. So we need to first compute its limits, okay? So what about its limit? We're given here this function when x is approaching 2. So we just rewrite this numerator in the parentheses of x. So here we have this function, okay? And we can also rewrite this one as in this form, x minus 2 times x plus 1. You don't need this step, okay? You can directly write that part. So if you simplify x minus 2's here, you will get x times x plus 1, and if you plug x equals to 2, you will get 6, right? So it means the function has limits at that point 2, and it's 6. But as you see, if you plug x equals to 2, you will get 0 in the denominator, so it cannot be defined by this. And you see the limit of the function is 6, so if we want that function f to be continuous at that point, its value should be equal to its limit. So we can redefine that function f of x by this. When x is not equal to 2, we just defined as before the function f. And if x equals to 2, we define it by its value, by its limit, sorry, at that point. So this new function, so we removed that discontinuity, right? So because this function has no value at that point, okay, but now it has, right? G of x now is this function, right, with this difference, this part, and this is continuous at that point, at the point a equals to 2, right? All right, now we will solve this one. We will use the intermediate value theorem, okay, to determine if the given function or equation has a root or not at the given point, okay? Here we have. So we first rewrite this given equation as in this form, just write all the terms on the left, okay? So we equalize it to 0, okay? Now, if we define this function f, you don't need to specifically to write like this, but it's more clear for me. Okay, just write f, which is defined by this equation, exactly the same function, okay? So it's defined on this interval, 1, 2, right? Okay, it's defined by this, the same equation. So now we have a function, okay? So we turn this out a function. So we have this function f, which is obviously continuous on this interval, right? There is no point which makes this function undefined, so it's continuous, okay? Now, we will use this intermediate value theorem. So first, see that f of 1 is this value, sinus 1 minus 1 plus 1, which gives sinus 1. And you know, from the graph of the sinus, you may say this, or I don't know what else you can say. Sinus 1 is greater than 0, We know this. And let's check for 2. You see sinus 2 minus 2. You get this value. Okay, so now we need to determine if this is less than 0 or not. Okay, so why is this less than 0? Look at this. We already know sinus 2 is in between 1 and minus 1, right? For any theta here, it's in between minus 1 and 1. Now, to get this one, sinus 2 minus 2, you can subtract 2, and you will see that this this value is less than 0, right? Just subtract from each limit or ending point, you may say. You will subtract 2 here. So for example, from this, you will get minus 1. So it means sinus 2 minus 2 will be less than minus 1. It means it will be less than, it is less than 0. Okay. So now we have f of 1, which is greater than 0, and f of 2, which is less than 0. Okay. Now, intermediate value theorem says that if on the given interval, you can find some value which is greater than 0 and some value which is less than 0 for a function which is continuous on corresponding interval, then it says that there is a root of the function between these points, these 2 points, 2 and 1. Okay, so now we know that this f of x for some, here I said a, you may say anything. So here for some a, f of a, we know that it's equal to 0 by the theorem. Okay, so it means f has a root on this interval, which is equivalent to say that this equation is equal to 0 for some value x on this interval. Okay. Now, you can understand this theorem, intermediate value theorem, geometrically like this. So you have a function, call it f here again. It says that f of x is first, it's our assumption. F is continuous on some interval. Okay. All right. And it says that, let's take this value also. See, okay. It says that if you can find some point which makes f less than 0 and another point which makes f greater than 0, then it should cut the x-axis if you find such 2 points. But here you see f of x is never less than 0 here on this interval. So it means f has no root on this interval, a comma b, as you see. Now apply the theorem here, because here we had not one of the assumptions, which is this. Okay, we couldn't find a point which makes f less than 0. What about here? You see between a and c here, for example, this one, take this value, you see f is greater than 0 here at that point. Okay, if you take this. And for example, for this, you see f is less than 0 here. So theorem says, as the function is continuous already, theorem says that between these 2 points, as the function is continuous, between these 2 points, you'll need to find some value which makes f 0. It means f has a root. As you see, we already have this point, this root of the function, right? Right, I hope it's more clear now. All right. Now the question 6. So is there a number that is exactly 1 more than its cube? So first, we need to write this sentence as an equation. Okay, then we will try to apply intermediate value theorem. Now, if there is a such number, okay, if there is a number who is exactly 1 more than its cube, then it should satisfy this equation, right? So x cubed plus 1 should be equal to itself, okay? It's 1 more than its cube, okay? Now we have this equation, exactly the same thing, right? Now it's a polynomial, so it means it's a continuous function on any interval a comma b for some values in R, for some points in R. Okay, it's always continuous. It means if we can find some value which makes this equation greater than 0, if we can find another value which makes this equation less than 0, then by using the theorem, intermediate value theorem, we will conclude that this function, this equation has a root. Okay, now just try a few values of x, a few real numbers, okay, to find such that the function makes this equation greater than 0 and less than 0, okay? So if we try x equals to 1, we see that the function is equal to 1. For x equals to 2, we get again something positive. We may use this or this, it doesn't matter. Now, what about minus 2? You see it's equal to minus 5, so it's less than 0. So now what did we do? What did we find? So if you say, ignore this part, if you call this function f of x, you see f is continuous and f of minus 2 is less than 0. And f of, for example, take this 2, or you can take 1. Let's take 1. 1, okay? So we found one point which makes the function less than 0 and one point which makes the function greater than 0. So the theorem says that there is a point between minus 2 and 1. There is a root of this function x0, okay? So such that f of x0 is equal to 0. So this equation, or this one, is equal to 0 for some value. We now know this because we had assumptions, okay, in this theorem. You can also say, for example, minus 2 and 2, okay? It doesn't matter, right? This interval is included in this one, so it doesn't matter. All right, now this part. So we will find limits, or we will say it does not exist. Here we have. Okay, we will evaluate limits. We have x squared over square root of x to the 4th. Let me write it. X squared over square root of x to the 4 plus 1. This is, here we have c. Okay. Now, what do we do now? As the limit is here, we see that x is approaching infinity. So we need to find something like this, some constant a over x to some power, x to the n, for example. Okay, because this one's limit is approaching 0 when x is approaching infinity, okay? If we can find something like this, it will be easier to compute the limit, okay? So here you see, we have in the denominator, we have x to the 4 plus 1. So we need to write here something in this form. So in the parentheses of x to the 4, we have 1 plus 1 over x to the 4. If you multiply them, you will get the same thing. So we have equality there, okay? Now, you can write this part outside of this square root, as in this form, of course, but you see x squared is always positive. So here we have this x squared, okay? Now what do we have? We can simplify these two and get this function. Now when x is approaching infinity, here we have 0. Thus we get in the denominator 1. Hence the limit is 1. Okay. So you just need to write something like this. Okay. Try to get something like this. When a is some constant. Here we had 1 for a. okay, and x to the x squared in the denominator, okay. All right. Now we have another limit to compute. We are given here a square root of 9x squared plus x minus 3x. Now we will again try to get some constant over x to the n. Okay, we will try to get something as in the previous one, but first we need to get rid of these squares. So we just multiply it by its conjugate. We say that this one it's conjugate because it's the same terms with the opposite sign. Okay, so we multiply it by this and divide it with the same. So if you simplify them, you will get the same thing. So we have equality again. Okay, now you multiply them, and here in the numerator you get this one. It's pretty simple to compute. Now what do we have? Here in the numerator we have x, and in the denominator we have the same thing. Now in the denominator, again, we play with the terms. So we write it in the parentheses of 9x squared. We have this one now. Okay, if you multiply them, you will get the same. So here we have this. Now we write this one outside of the integral. So we have this absolute value of 3x. Okay. Now what do? We see that x is approaching infinity. So here we have something positive inside of the absolute value. So we have this 3x. Now in the parentheses of 3x, we have this denominator. Okay, we didn't do in the numerator anything. So we simplify these x's and we get 1 over 3 times this one. It means it's 1 plus 1 over 9x in the square root plus 1. Okay, the same thing. Now when x is approaching infinity, this is 0. So we have 1 plus 1 times 3. Okay, so in the denominator we have 6. So we get 1 over 6. So we multiply first it's by its conjugate and divide it with the same. Okay, so we tried then to write in the denominator all terms in x to the n, or a over some constant over x to the n. Okay, we tried that, x to some power. Okay, we tried that, and we wrote this one outside of the square root, and as x is approaching infinity, this is inside of the absolute value. We have something positive, so we have this. Okay, the rest is easy. All right, let's find this one too. This will be the last question. Okay. Now we have, this is the part G, yes, 7th question. So we have this one, minus infinity plus 4 over this. Okay, so here we have x is approaching minus infinity. Okay, so inside we have something negative. So we multiply it by negative to write it outside of the absolute value. So what do we have? At minus x cubed, which will give minus x cubed again, plus 4. Now what do? We need to write this one. We need to have something constant in the numerator and x to the n, right? So in the parentheses of x cubed, we have first the limit. In the parentheses of x cubed, in the numerator, we have 1 plus 4 over x cubed. Just multiply them, you will get the same. Okay, and here in the denominator, what do we have? Let's take it again, write it as in the parentheses of x cubed. We have minus 1 plus 4 over x cubed. Okay, Now just simplify these two. Okay, so we have limit of this 1 plus 4 over x cubed over minus 1 plus 4 over x cubed. When x is approaching minus infinity, here we have 0, 0. So we have 1 over minus 1, which will give us minus 1. Okay, that's it. All right. So if you have any question from the first 7 questions, you can write me an email, of course. Okay. So we will start with the question 8 next week. Okay. All right. That's all. See you.